Okay, so let's talk a little bit more about hydrogen bonding, just to make sure you fully understand this concept, because it is such an important concept in chemistry. For those of you who go into organic chemistry, you will see hydrogen bonding all over the place in organic chemistry. You'll see it in biological chemistry, talked about in biology as well. Okay, so let's take a couple of the molecules. Let's take that molecule. Let's try not to draw too sloppy. Okay, so if we take these two molecules, which has a higher boiling point? So the question you want to ask yourself is, go through the intermolecular forces, hydrogen bonding, dipole, dipole, van der Waals. Can it make hydrogen bonds? If yes, stop there, because hydrogen bonds is the most important. If it can't make hydrogen bonds, then does it have a dipole? If it has a dipole, yes, then stop there, because dipole is the next most important. If it doesn't have a dipole, then you have to go to van der Waals attractions, the weakest. So in this case, two molecules, can they make hydrogen bonds? And the answer is yes, both of them can make a hydrogen bonds because of the OH. All right, so both molecules can make hydrogen bonds. So in the last lecture, so this molecule is methanol. We looked at what its hydrogen bonds look like. This molecule is ethanol. So what does this hydrogen bonds look like? So we could draw that for the carbon chain, right? 2 carbons, 1, 2, and then it's attached to oxygen. So if that molecule made hydrogen bonds, so just line up the OH. Line up the partial positive hydrogen with the oxygen in another molecule, and partial positive hydrogen with oxygen. So that can make hydrogen bonds just like that. So they both can make hydrogen bonds. So hydrogen bonds is a wash. So you can't use that to figure out which one has a higher boiling point. So what could you use is, since hydrogen bonding is a wash, then you have to go to secondary forces and van der Waals attractions. So this has more surface area. So since hydrogen bonding is comparable between the two, then you could go to surface area. The one on the right has more surface area. Ethanol has more surface area than methanol, so it's going to have a higher boiling point. So ethanol's boiling point is 78 degrees Celsius, and methanol's is 65 degrees Celsius. Okay, let's take these 4 molecules. And let's put them in order of boiling point. And let's identify the main type of intermolecular attractions that each one would experience with another molecule of itself. Okay, so let's say highest boiling point equals 4, and let's say lowest equals 1. So we'll call this A, B, C, and D. Okay, so let's identify first of all which type of intermolecular attraction each one can experience. So A, can it make hydrogen bonds? And the answer is no, because it does not have a partial positive hydrogen, because all of the hydrogens are on carbon. Right? Does it have a dipole? And the answer is no, because all of the atoms, no atom has a partial positive or partial negative, because there's no big electronegativity difference between carbon and hydrogen. So this can only have van der Waals attractions. Molecule B, obviously we just looked at this, has an OH, it can make H bonds. Can molecule C make hydrogen bonds? And the answer is no, because these hydrogens are on carbon. They're not on oxygen, so the hydrogen is not partial positive, right? Because those hydrogens are attached to carbon. So no H bonds. because no partial positive hydrogen. Does it have a dipole? Well, yes, it has a dipole, because that's partial negative, that's partial positive, so that molecule has a dipole. So this molecule will have dipole attractions. And this molecule D has H bonds. So which will have highest boiling points? B and D. And we just looked at in this example, since they can both make hydrogen bonds, then you could go to surface area. D has more surface area than B, so D has the highest boiling point, so it's 4, it's 78 degrees Celsius. And B is next, so it's 3, it's 65 degrees Celsius, if you determine those experimentally. And then between C and A, which would have a higher boiling point? Well, dipole-dipole attractions are stronger than van der Waals attractions, so C would have the next highest boiling point, so it's number 2. It's negative 19 degrees Celsius boiling point. And A would have the lowest boiling point, so it's 1. And its boiling point experimentally is determined to be negative 89 degrees Celsius. All right, so A and C are both gases. Van der Waals attractions and dipole-dipole attractions not that strong. B and D are both liquids, because hydrogen bonding is very strong intermolecular attraction. Okay, let's take these molecules. So let's put them in order of boiling point. So we'll call that A, B, C, D, and E. Okay, so which one's going to have the highest boiling point? Which one's lowest? So we'll say highest equals 5, lowest boiling point equals 1. Okay, so which one's lowest? So what type of intermolecular attractions can they make? Well, they all have an OH. So they can all make hydrogen bonds. So that's a wash. So then you could go to surface area. Well, this has 1 carbon, 2 carbons, 3 carbons. This has 4 carbons. And this also has 4 carbons, right? Because that's 1, 2, 3, and 4. Okay, so the lowest boiling point would be A, right? Only 1 carbon. And then the next would be B. And then the next would be C, because those have 1, 2, and 3 carbons, so least surface area. So A's boiling point again, whoops, 65 degrees Celsius, 78 degrees Celsius, 3 carbon chains, 97 degrees Celsius. And then how about between D and E? They both have a 4 carbon chain. But if you compare these two, right, E has a branched carbon chain. So if you remember from the van der Waals attraction discussion, as you increase branching of the carbon chain, decrease boiling point, because surface area decreases, so van der Waals attractions decrease. So E is going to be lower than D. So this will be 4 and this will be 5. So 4 carbon chain E is 83 degrees Celsius and D is 116 degrees Celsius. Okay, let's compare these molecules. We'll call it A, B, C, D, and E. So again, let's put them in order of boiling point. So 1 equals lowest boiling point, and 5 highest boiling point. Okay, so first of all, what do A, B, and C have in common? Well, so first of all, they are all, right, 1, 2, 3, 4 carbon chain. 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. So they're all C4. And if you count the hydrogens, so there's 3 hydrogens there, 2 hydrogens there, 2 hydrogens there, 2 hydrogens there, 1 hydrogen there. So 3, 4, 5, 6, 7, 8, 9, 10. So they're all C4H10O. So they're all what are called structural isomers. Okay, and then B has 2 carbons, and oops, I drew E wrong. And each oxygen, of course, has 2 lone pairs. At some point, we stop drawing lone pairs, and we just, hopefully you recognize that they're there. Okay, so, and then E has 3 carbons. Okay, so which do you think would be the highest boiling point? The ones with 4 carbons, or this one with D with 2 carbons, or E with 3 carbons? Well, so they can all make hydrogen bonds, right? But E has 3 places, OHs, that it can make hydrogen bonds with, and D has 2 OHs that it can make hydrogen bonds with. So the more hydrogen bonds you can make, so between similar molecules, the higher the boiling point. So E is going to have the highest boiling point. Right, this molecule is one maybe you're familiar with. It's glycerol. So if you've ever worked with glycerol before, it's first of all, it's a very viscous molecule. Why is it so viscous? Because it can make lots of hydrogen bonds. Right, so it's a very sticky molecule. Those hydrogen bonds, the molecules are not going to want to slide by each other very well. So, and it can make lots of hydrogen bonds, so it's going to have a very high boiling point. It's 290 degrees Celsius boiling point. So molecule D with 2 OHs that can make 2 hydrogen bonds is going to be the next highest boiling. It's 195 degrees Celsius. This is a molecule maybe you're familiar with as well. It's called ethylene glycol. Right. Also known as antifreeze. So where do you find antifreeze used at? It's in the radiator of your car. You know, what's the purpose of a radiator in your car? It's to help cool the engine. Right. So this molecule can absorb a lot of heat, and it also helps to suppress the freezing point, to keep the water from freezing, to keep your water lines in your radiator from freezing over during the winter. Okay, and then between A, B, and C, so these molecules all C4H10O, which will have the highest boiling point. So they all only have 1 OH, so they can all only make 1 hydrogen bond. So hydrogen bond needs a wash between them, so then you would go to surface area. So A has the most surface area, it's the most linear, so it's going to have the 3rd highest boiling point. So it's 117. And then the next highest would be C. So it's got 4 carbon chain, but the OH is on the 2nd carbon, so it's more branched. It's 98 degrees Celsius, and then B only has a 3 carbon chain. So it's got a branch in the middle, and the OH is in the middle as well. So it's going to be the lowest, so it's 83 degrees Celsius. Okay, a couple more examples. About H2O versus H2S. So which will have a higher boiling point? Well, so first of all, where's sulfur at in the periodic table compared to oxygen? So boron, carbon, nitrogen, oxygen, fluorine. So sulfur is right below oxygen on the periodic table. So which is more electronegative? So you don't even really have to look up electronegativity values if you just know where atoms are at in the periodic table and you know the trend. So as you go up the periodic table, so as you go up a group, electronegativity goes up, right? So oxygen's more electronegative than sulfur. But the values are 3.44 versus 2.20, so a difference of 1.24. And oxygen's periodic, sulfur's electronegativity, I do not have in my notes, but it's not much different than hydrogen. So in this case, oxygen is very partial negative, and hydrogen is very partial positive, whereas for sulfur, it's very small partial negative, very small partial positive. You know, so which two molecules would be more attracted to each other, H2O or H2S? And of course, it's going to be H2O. So they're going to make very strong hydrogen bonds, whereas H2S, because of the very small difference in electronegativity between hydrogen, carbon, and sulfur, they're going to make very weak hydrogen bonds. So the higher boiling point would be water, right? It's got 100 degrees Celsius boiling point, whereas H2S is minus 60 degrees boiling point. So it's a gas at room temperature and water is a liquid. So H2S is it's a toxic deadly gas. It's one of those gases that miners used to have to, miners have to worry about. So how do miners used to detect toxic deadly gases? Right. They would take a bird down in the mine with them, a canary. If the canary died, it means it's time to get out of the mine because there's toxic deadly gases in there. Nowadays, they would just have electronic sensors that could tell you if the toxic gases were present or not. Okay, one more example. So take water versus ammonia. Which one will have a higher boiling point? So which one can make stronger hydrogen bonds, basically, because they can both make hydrogen bonds. And again, we just said 3.44, 1.2, so a difference of 1.44 in electronegativity. So oxygen's very partial negative, hydrogen's very partial positive, and nitrogen's electronegativity, not in my notes again, but I think it's a 3.04. Right. Am I doing my math wrong? I think I'm doing my math wrong. Totally wrong. That's a 4, that's a 2, that's a 2.24. Oh, it's 2.2. Hydrogen's 2.2. There we go. That's better. So for oxygen and hydrogen, difference in electronegativity is 1.24. And NH's, I think, is 0.84. So yeah, so even though ammonia can make more hydrogen bonds, each one is weaker than OH's hydrogen bonds because of the bigger difference in electronegativity. So water can make stronger hydrogen bonds. And that's going to be reflected in its boiling points. Water's boiling point's 100 degrees Celsius, whereas ammonia is negative 33 degrees Celsius. So it's a gas also at room temperature. Okay, so OH's bonds are more polar than NH bonds, so they're going to make stronger hydrogen bonds, and that's going to have a greater impact on boiling point. And that's it for hydrogen bonding.